We're going to talk about how we detect objects on an image, looking for the features on the image. You take those features and you combine them in some way, and then you can make some predictions, right? That's supervised machine learning. We're going to talk about supervised machine learning, right? And we're going to really answer this question, that is, how does supervised machine learning work? Now, the kind of interesting thing here is that I wanted to give you this thought process. That is, guys, you already know about supervised machine learning. You probably use this like probably every day. And I want definitely make sure that you're not afraid of these different concepts. Okay, raise your hand if you know about curve fitting. Curve fitting. Let me describe that to you, and that's exceedingly simple. So basically, you have this, typically, right? This is example that's done in the two-dimensional space. You have this y versus x. So you take some measurements, right? So for example, you would take some measurements such as, you have like a stopwatch, right? And you have a metal ball or something. You go to the top of the building, okay? And you're measuring essentially, right? That is, if I have this clock and every single, 100 milliseconds or so, I want to measure the distance of how far the ball dropped. That's it. That's all that is, right? We want to measure how far the ball dropped. And then you come up with this graph, okay? So the x-axis would be time, y-axis would be, how far the ball actually dropped. So all the red dots, all the measurements. Meanwhile, the dots are spread around a little bit. Wind resistance, maybe someone is like, maybe the wind is blowing, maybe, I don't know, maybe the metal ball is still too light and, the wind resistance was huge, right? It could also be a measurement error, right? That is, how do you measure this ball goes to, to the ground? Maybe there's some measurement error. What in reality is, data is messy, right? So you have these data. And then what you want us to do is basically, okay, we need to basically fit this equation, right? Y equal to ax squared plus bx plus c. We're going to fit this into this line here. And our job, if you learn about curve fitting, is just trying to find A, B, and C, right? It's trying to find A, B, and C. So it's almost like given this data, let's find a function that fits the data based on some criteria, right? Guys, once you find this blue line, right? So visually you can just adjust this blue line, left and right. Oh, I got it. And just say you got it. If you have the blue line, what would this enable you to do? You can make predictions. You don't need to go ahead and measure, right, how far the ball actually fall down. As long as you have the time, you know exactly. I mean, you don't know exactly, in theory, where the ball should be, right? That's called prediction. You know what this means? This means that you can understand machine learning, okay, supervised machine learning equally well. And guess what? We have been using the curve fitting to understand our world, right? Have you guys heard about this experiment called LIGO? So it's Laser Gravitational Interferometer Observatory. So LIGO is something where you guys know Einstein, right? And Einstein's general relativity, right? You learn something where, gravity is make the space-time, curved. Now, the thing is, once you have a huge kind of explosion, of these metals in the universe, what happens is there's also this thing called a gravitational wave. So it's almost like you throw a huge rock, right, into a pond, right? Like a pond was very calm, you throw it to the pond, and then you see waves coming at you. By looking at the waves, maybe you can guess maybe where that rock landed and, like how heavy the rock is. So what LIGO did was basically be able to measure this event where you have two neutron stars trying to attract each other in the spiral, and conservation for angular momentum. That's essentially what we're measuring for two neutron stars. What's crazy about this experiment is that the distance they measured, because these effects are so small, that's why they have to build two identical apparatus. And these things are, huge. We're talking about the arms of it is 4 kilometers long, right? Huge. What's the diameter for hydrogen atom? It's 0.1 nanometer or 10 to the minus 10 meters. Do you know what's the size of a proton? The proton is 10 to the minus 15 meters. What they're able to measure is 1 in 1,000th of the proton size. So we're talking about 10 to the minus 18 meters. That is impressive. But this is, of course, decades of research and maybe tens of millions of dollars, tens of billions of dollars. Construct some understanding of the nature, right? Your prediction, and try to fit essentially if that data and the model, you would see if you can find an equation that really fit this data. And how do you know it fit? You look at down there, you see the residual. The residual are essentially like a random white noise. They distribute around zero, they go up and down. It's not like there's any pattern. Then we claim, oh yeah, we understand the world. This is essentially how science was built, how science was learned. And this is the reason why we have all these conversations today, because without the advancement of these things, we won't be able to build computers, let alone learning about machine learning. When you think about it, what kind of criteria do we need to have for us to say find A, B, C, that ax squared plus bx plus c, kind of story? It's actually pretty simple, right? It's like you look at basically that curve and the distance between all the dots and those curves, and you try to minimize the sum of that distance. Actually, you're trying to maximize the difference between y1 minus the predicted value, right? Square that and add all that together. Have you ever wondered why we just not using the cube? The positive of the cube is a positive. The negative cube is what? Negative. So when you add together, what happens? They cancel each other. You don't know how far these dots are. They don't really like fit the dots at all for the cube. Okay, so there's a reason why we go for the square one, and that has to do with maximum likelihood. So maximum likelihood is something you probably will learn later. Basically, it says that if we can generate this curve based on the square thing, then what happens is if we allow this different noises come into play, then this curve would be the best model to generate these data. All right, so I know probably only 5% of you got that concept, but that's okay. Just remember maximum likelihood, and later on, you can revisit this, okay? The important concepts in supervised machine learning, there are two most important concepts. One is the predictors, right? So those are, for example, features, right? So predictors are variables whose pattern you mine to uncover insights, okay? And whose value will be used by the model to compute a value for the target. So that could be the time that you measured, right? In that ball dropping kind of experiment. And the target is the variable whose future value you want to predict. So that could be how far the ball actually dropped. And when you think about curve fitting, the goal, right, based on observation, find a model to predict the future. Supervised machine learning is based on the input-output pairs, right? This is the picture for the sad. This is a picture for angry, right? Find a model that predicts the output given the input. So then you don't have these, emotion data. You just say there's a picture. Can you predict that's a happy, sad, surprised, or angry? For the curve fitting, X is called independent variables. For supervised machine learning, it's called features or predictors. For the curve fitting, Y is called dependent variables. And in the supervised machine learning, called labels or targets, right? Supervised machine learning, you can actually be any model, whether it's like a linear regression model or some very complex model, okay? It could be a probabilistic model. But for the curve fitting, it's any function, right? You see the similarity? Okay, so I'm going to give you some examples to really concretely illustrate this. So we actually had a guest speaker. His name is Glenn Solomon. So he invested this company called Open Door. And the Open Door is this thing where, buying a house, or, selling a house used to be a very daunting effort, right? But in Phoenix, Arizona, people have this option to basically input their home address. And this website, opendoor.com, will basically give you this offer right away without seeing your house, right? You can actually click accept, right? And then they will send a few people doing the post, inspection, that kind of stuff, and they're going to wire you the money, okay? As you can see here, the goal would be you make an offer to the homeowner, right? That will be accepted, right? Without seeing the house though, right? And the X would be all the predictors, right? Would be, how big the house is, how many rooms you have, what's the location, right, etc. And then the thing you're trying to predict, of course, is the purchase price, okay? And the model here, we can actually start with a regression model, for example, linear regression model. So regression would be something, for example, a linear regression. It's just almost like ax plus b. Those x's can be like a times square footage plus b times rooms plus c times, maybe the somehow you can quantify the zip code, right? Maybe plus d, whether you have high power lines above you or not. You see that? It's basically a linear combination of all these features, although you turn those features into numbers though. And we turn all those things into a number, multiply by a factor, add all that together, and then we can predict something. And your job is actually finding these parameters, the factor you multiply by, adjust them lower and higher so that you would predict the output. Okay, I'm going to continue. All right, here's another interesting supervised machine learning algorithm, although I don't know what's behind it. How many of you watch at least one YouTube per day? You know what, I think other than self-driving, YouTube recommendation algorithm is one of the most understated application of AI. I'm a big fan of Kobe Bryant. The day I got the news, I was very shocked. But, I'm watching Kobe Bryant, incredible, impossible shots. Right? Sometimes you see this guy doing fadeaway and 4 people are defending him. That's not exaggeration. That actually happened. And then you can see up next, Kobe Bryant top 50 all-time plays. I'm like, how can I possibly resist that? So the goal, right, would be maximize my time to watch on YouTube. Sounds like they succeeded for all of us. You all raise your hand. And the X would be what's the current video, or maybe my historic watched, right? Maybe demographics. And the predictor is that, are you clicking the next video or not? What are other features you can think of? The name, yeah. What about the number of likes? The views, right? If the more views you have, maybe this is good video, high quality video. Trending keywords, who do I liked? Maybe I watched LeBron James, and therefore you must also like Kobe Bryant. Maybe it's like this is a political campaign. You watch maybe like Barack Obama, like 2008, right? Which I do. And then they would never recommend any Trump videos for me, right? You see that? And so there's another important thing here I didn't talk about. A loss function is essentially to look at how far away you're from the truth. And then you can use that loss function to adjust your parameters. Later, we're going to touch up on this quite a bit. Here's another one. So that is step number 1. You find out where the tests are. Let me give you a demo. This is one of the stuff that our students built, right? This is called the candy informant. Basically did research in terms of candy, okay? Give every single candy a numeric score, okay? And then, have all these bad ingredients, and we rated them, okay? So this is like machines read hundreds, thousands of these articles and give a numeric score. So we're gonna find some images and posters, maybe this one. And then this candy informant can actually do OCR. Did you see that? Black Lives Matter. OCR means optical character recognition, right? You can have even more complicated stuff. You can read out this. But this is something our students built. And it's actually a supervised machine learning model. So first of all, it has to have 2 stages. You need to identify where are the text. So for example, we wanted to help people purchase stuff faster. So instead of, for example, having them to key in for credit card numbers, you can basically just like upload an image and we can, fill in the numbers. And the way to do it is, first of all, look at where the letters are. Once you have all these, letters or characters, then you can distinguish what kind of letters they are. Okay, so that's another example, okay, of supervised machine learning. And both cases, both steps are supervised machine learning. As a matter of fact, of course, the object recognition stuff that you guys are working on, those are supervised machine learning model. So supervised machine learning model, as I said, is more than just regression. We talked about regression, whether it's about housing prices, YouTube recommendation video, although I don't know what's the model. We could also have classification. That is, you're trying to predict discrete outcomes. And when you think about, for example, the stuff you're working on, it's actually more than classification. It's not, for example, you give a photo and you tell what kind of emotion this is. You have to also identify where that emotion is, or multiple object possibly, right? That's object detection. That's actually more than classification. But classification is predicting discrete outcomes. For example, regression would be like, what's the temperature tomorrow? And that would be a number, a continuous number, right? Classification is discrete outcomes, code or not code. That's it. That's classification. Just like how we talked to you guys about how to build an AI product, now we're going to actually dissect how do you create a supervised machine learning model. As a matter of fact, you're going to go through these steps yourself in code. So it's a good idea, for you to actually take note of this one. So first of all, of course, if you don't have good data, you're not going to have good AI. So you wanted to get good data and lots of it. And then second, you want to explore the data set for understanding. A lot of people, they don't try to look into the data set and really understand these features. They just like shove everything into a model, and then their model doesn't perform, and they don't know why. So it's super important for you to have the data analysis skills for you to go for understanding. Remember, we did a couple of things last week. We examined the data, right? The COVID-19 stuff. We did a whole bunch of data visualization. Although, we didn't have enough time to go through it, but later on you will see the data visualization and data exploration is one of the most crucial skills if you wanted to become a data scientist. Third step, we want to clean the data, because real life data, they're never clean, right? They're never clean. You could have data not consistent, data missing, right? How do you deal with those? You also want to engineer the features, for example, in the COVID-19 case, instead of just using converted number, obviously that number depending on the population. That's why we have the confirmed number divided by the population to normalize it. That's engineering the outcome. But the features could be also like the percentage of people who have more than or equal to college degrees, right? That would be a feature for education. We also engineer a feature for poverty. We engineer a feature for unemployment, right? Normalize against the population, you have all these rates. And that's how you're going to predict the fraction of people who are infected by COVID-19. Data will give us insights. And then once you have all these features and everything, now it's time to try various models. You try different models and see how they perform, okay? And lastly, you want to evaluate the results and choose the parameters, and there are trade-offs to be made. Again, input-output pairs. The goal is trying to predict the offer. Input would be the X, like the square footage in rooms. Y would be the prices. So I'm going to use this one as example, right, to illustrate these steps, okay? And when you think about it, so the raw data of predicting the purchase prices, you see those numbers. What is the class? What is the zoning? What is a lot of footage, a lot of area, the street, the alley, the shape, utilities, fence, month sold, year sold, sales price, sale condition, and sale price. First of all, these data, can you use the utility thing? It's all pub. Can you use that as a feature? They were just text information, right? Remember these models, they need to take numbers, right? So somehow we need to translate that into like some numbers. So this could be like utility, could be like public, could be maybe private. So then we should maybe give a score. Maybe the public ones, we know they're supported by public, maybe it's 1. And then, all the utilities that are private, we'll give it a -1 or give it a 0. So constructing features from raw inputs, as I said, for example, the sales condition, right, the 0 or 1, you turn all these text information into numbers. The fence or pool value goes up, right? Month sold or year sold, plus the how much time between the last sale price and, or the inflation rate, you can predict the sales price. This is why you need to explore the data set before machine learning. So these are data exploration and visualization. Do you guys see the math for AI slide? There's this thing called distribution, and this is distribution of sales price. So what can we tell about the sale price for a house in the United States? The most likely, right, you're looking at houses that are under $400,000, between $100,000 and $200,000. So real life data, as I said, is never clean, right? So for example, you could have missing values, unbalanced data set. I'll talk about why unbalanced data set is a pretty bad, right? Or basically intuitively, you just don't have enough example for one class versus the other, right? Missing values, Brandon will talk about that, right? And then we also need to do this train and test data split. So basically what you do is you split the data into, maybe like 80 by 20, 80% for training, right? You basically take that training set and the X's, the Y's. So you're trying to adjust the parameters, right? So that you can predict Y, right? Using that training set. And the testing set is you treat it as the data in mail. That is, you never actually see them. You never really use them for training. Only when the model is trained, right? Then you use that test data set for once to see if the model is performing or not. So basically using the test data set as the real world situation, except that you know the answer. So then you can use that answer to know whether your model is performing or not. I'm just gonna fly through this, but you know what? We're gonna look at it, later in code. You can see the first line here, right? Train, test, split. You take all the data, you come back with X train, X test, Y train, Y test. And then we define linear model, we call linear regression model, right? Take the training data, your output would be the model, right? And then your prediction is you basically using the model to predict, but this time you only take the X test. You don't take the Y test. You use the Y test to look at how wrong or how right you are. You know what? This whole thing could be like, wow, it's still hard, but you know what? We're gonna go through it line by line, okay? So how does the model train and minimize the loss function? So basically, we're gonna do this thing called a gradient descent. So the way to think about it is, you can see, this graph on the right hand side. Maybe you're trying to find those W's to really minimize the loss, right? The loss would be how wrong you are. And the way to do it is sort of like, you look at where you are at the point, and then you go to the opposite direction of your gradient or just the slope, okay? And then gradually, once the gradient doesn't move anymore, you're like, okay, I'm probably finding a local minimum there.